So, hi everybody. Glad to be here again. It's a bit chilly, isn't it? But on the other hand, it's a bit unfortunate. On the other hand, if sun would be shining, it would be unbearable hot already in here. So, I'm not sure which is the worst of the two worlds that we could have. So, welcome to the talk, and I won't bore you with that, but I will start with a little bit of apology because when I discussed the talk with Feller and I told him the shortest time to deliver this talk usually is about 60 minutes. The longest version I ever gave is 2.5 hours of that talk. No, you don't have to wait for 2.5 hours today. So I promised to get through in 45 minutes. Unfortunately, I have to cut a few corners for that. But I will tell you when I'm going to cut the corners. And I also will use up the Q&A time, so another sorry about that. But I will promise you I will go to Slido afterwards and look for your questions and try to answer them as good as I can, or just get a hold of me on the conference. I will be here till tomorrow evening, and I will be happy to have any discussion with you about the topics. So much of apologies. Now let's walk into the talk. So, welcome to the wonderful and marvelous world of microservices. I mean, we are all doing it, or at least we would love to do it, even if our company does not allow us to do that. But microservices, and let's assume for a second you're doing microservices. And it's, microservices. And of course, if you do microservices, you put them in Docker. Yeah, Docker. Another, Docker. And then what else could you do with a container? You put that in Kubernetes. I mean, there are a few people around who still do Swarm, but let's be honest, Docker won the race. Kubernetes won the race. So Docker, Kubernetes, microservices. So in other words, you're doing it the cloud native way. I mean, that's a little bit disheartened definition which the Cloud Native Computing Foundation gave us. So basically what they were saying, if you're doing microservice and put them in Docker and run them on Kubernetes, you're doing it the cloud native way. So you're all cloud native, And so while you're still celebrating yourself, this is the time when grumpy old man, that's me, comes along and then asks this question. Well, that's cool, but have you ever pondered the consequences of going cloud native? And people know I'm a little bit nasty guy, and so they, what? And I'm cautious, why are you asking that? I say, let's be cool, but let's discuss the consequences of cloud native computing for a second. So you're going cloud native, which says you make services and put them in containers, and which means that you have different processes as runtime, which of course means there's some remote communication between the services. So what you just did is you created a distributed system. And now the few of you who are not allowed to do microservices yet think, I'm good, I'm fine. I'm not touched by that. So let's enjoy the rest of the talk. Unfortunately, sorry about that, guys. Cloud distributed native systems are no longer limited to cloud native computing. Basically, all systems you're working on are distributed these days. So chances are that the software that you develop and maintain is part of a big distributed system. I mean, even the most conservative companies, so some people said that insurance companies are rather conservative. I mean, they always have this partner system, which you always have to ask for any customer and client information and so on. And it's a remote call, and you of course have the directory server, and your database, also remote call. So you're working on a distributed system. And in microservices, you're working on distributed systems to the square. Well, and this has a few consequences. So let's first go with a little definition of distributed systems as Werner Vogels, the CTO of Amazon, made that before. That's distributed systems in a nutshell. Everything fails all the time. And why is that happening? Reason is there are some failure modes in distributed systems that you don't see inside a process, like that the other side is no longer responding, or that it's sometimes responding, or is responding but terribly slow, or just gives you the wrong answer, so think eventual consistency. So yeah, it will be the right answer eventually, but at the moment you get the wrong one. Sorry about that, or that the other systems just went amok. So nasty kind of failure mode that you see. And this leads to some consequences which you will see on the application level, like you don't get the answer, or you get part of it, or it's distorted, or you get it twice. So you just ordered your refrigerator twice. Oh, sorry about that, but you will find a place for it. Or out of order, so the withdrawal is before the deposit and all that stuff, and then this partial out of sync local memory, which is, okay, my truth on my machine is a different truth than the other machine has, which happens all the time. And is your application prepared for that? And unfortunately, whenever I talk to people who are working with microservices because it's so cool, they're never prepared for that. So they program a distributed system in a way as if it were a local system. But let's wrap that up for a moment. So the effects I just talked about is this non-deterministic behavior which you get due to the remote communication because you distributed stuff. If you were inside a process, you wouldn't see that. So your process either lives or is dead. And every one your calls and you get answers, and there's not that latency thing and so on. So it's a lot easier. Okay, with multi-threading you still can screw it up, but it's still okay, basically. So in other words, remote communication, these are the predetermined breaking points of your application, and it will hit you on the application level. Now, we don't like that it breaks all the time and so on, because, I mean, eventually the customer will be affected by that, and we don't want to make customers angry. We want them to be happy, and so we try to do something against that. And there are some ways how we typically try to handle that. So first thing is, so blast from the past, let's buy some expensive high availability hardware, which isn't too bad if you have a very small installation with just a few nodes, 2, 3, maybe 5, but 5 is getting hard. So probability of things going wrong may be low enough that you can get away from that. In a cloud environment, you don't have HA, so, well, and most of you are running on a cloud, yeah, okay, forget about that one then. Or you say you delegate that to the infrastructure. I mean, that's what we developers were doing for 40 years now. So let the infrastructure handle it, and we assume that we're just programming a single process. These days, that is basically, yeah, there's Istio or Linkerd or something like that, which is a cool thing. The problem is it just has one response mode if something does not respond or so on. And just assume you're in the evening, at the party, at the reception here. And so the one situation is you go to ask your peer, hey, how did you feel about the weather today? Wasn't so good, was it? And so on. And peer doesn't respond. And the other situation is, somebody fell down there. I think that person got a heart attack. So could you please get a doctor and try to do first aid? And that person doesn't respond. And you have just one way to redo it in both situations. So either you scream at the person because that person didn't respond to your weather question, or you say, well, I guess, so probably this person's going to die, so let's have another drink, and so you need different kinds of response patterns from the application level. So you implement all that stuff on the application level, which is good thing. So all these resilience patterns and so on, lots of them, you heard about them, and you implement that on your. Still, it helps, but it doesn't fix a broken design, a broken functional design. Like here's a service A, get a request from the outside, and just to answer that request, it needs to reach out to a service B, which is not facing the outside, so like getting some data or something like that, and then Service B is down, and unfortunately you can't complete your request. So you can build all these circuit breakers in between, and they're just telling you, oh, sorry, you're also dead. So you just build a non-resilient system, which means you have to touch that or to address this thing on the functional level. So how you design your functionality, how you split that up. And while doing that, because remote communication points are your predetermined breaking points, you try to minimize these. Okay, let's try to do that. So basically there are two options to do that. One is having less artifacts. The other one is getting the communication right. This one is the harder, by the way. But first, let's talk about that one for a minute. You remember that one? First law of distributed objects, don't distribute objects. And Martin Fowler, 5 years ago, wrote, discussed that in the context of microservices. Cool post, read it if you like. I give you my short version, my short recommendation. If you can get away without splitting things up, just do it. I mean, everybody thinks, I talk about the deployment monolith. Everybody thinks, oh, the monolith is necessarily a big ball of mud. No, you're still allowed to structure it well. And I mean, if you're not even able to structure a monolith well, and then you think with microservices everything will be fine? Wow, that's a bold bet. I haven't anyone seen to win that bet yet. So big ball of mud, now you have a distributed big ball of mud, so the worst of two worlds. That's cool. And by the way, Etsy proved that you can create a monolith which is well structured, or which you can deploy 50 times a day. So it's possible. It's just a bit of discipline that you need for that. And I say, if you can get away with the monolith, because it's the easiest deployment format that you can have. One process, running, not running, load balancer and so so straightforward. Microservices are a lot harder. You heard lots of sessions about that. Unfortunately, your domain will be a little bit too big for putting everything into a single monolith. And even if you would be able to do that, there wouldn't be any machine to run that. So you have to split that up in some way. And here are my rule of thumbs how to do that. 95% when to split up things is when you really need independent deployments. There are several reasons why you might need that. But if you really need that this piece of functionality can be deployed independent of that one, then you need to split things up. And by the way, there's a lot more than just writing a microservice that you really can deploy things independently. There's such a line of things that you still have to do that you really can deploy independently. Most of the time, when I see microservice installations is like, yeah, here's my distributed monolith, let's deploy that twice a year. Yeah, they're trying to do that more often, but it's so hard, and you know the stories. Or, and that's the other 5%, if your non-functional requirements for the different parts of functionality are so disparate, so different, that it really makes sense to put them into different types of architectures or solutions, like security, very specific security requirements for this part of the functionality and very hard to meet, so PCI DSS and all that stuff. So you want to put that away and not have certification for all that, or reliability and all that stuff. Unfortunately, most of the time, the people forget the security all the time, and reason about scalability, we need microservices for scalability. And I asked them, okay, let's take an old LAMP stack server, which cost about 3,000 to 5,000 euro. And you can, if you set that up and configure that properly, you can run about 6,000 users concurrently on a LAMP stack, and without going down, without any problems. And if you write the application well, then you can put a load balancer in front of that and say have 10 instances, so 60,000 users in parallel. Do you have a use case that requires more than 60,000 users at the very same time? I mean, back in 2001, I had a customer with 10 million online users on their self-service solutions, and we ran it on one server because there were never more than 3,000 or 4,000 users logged in at the same time and running requests. I mean, that's even if 100,000 users are logged in, usually they're not sending a request all at the same time. So whenever you feel tempted to say you need microservices because for scalability, then just try the sentence, I am not Netflix, I am not Netflix, I am not Netflix. It helps a lot. So if you're Netflix, go along, show us the new cool stuff. So much about more coarse-grained components. Now let's go to the hairy stuff, which is a little bit harder. And to introduce that, I use a little case study, which is quite straightforward. So e-commerce, everybody knows that in some way. So just basic use cases, which is this searching and showing some products, adding the shopping cart, checkout, shipment. And so yeah, payments, we assume that payments would be easy. We all know that payments is not easy. It's all this going forth and back and forwards on the browser. And, it sucks, yeah, I know. But let's assume it's just one remote call and you're done, and no recommendations is all that stuff. Very simple. Right? And before we go into the design of that, be aware, checkout is where we make the money with, and shipment is where we make the customers happy with. Important. And now, typical design that I see all the time happen. So I describe that in hindsight. So usually design is going forth and back and in all directions, and eventually some design emerges. Even if they do a big design up front, it still emerges in some way. It's just a little bit uglier. That's the difference. But if you look at hindsight, what happened there, and it would be something like that. So people start with, yeah, avoid redundancy and maximize reuse. Our architects told us so for 40 years, so don't do that. And then they start with some kind of domain model. I mean, before that, we called that entity relationship model or object model, and now it's domain model. It's just a fashion. So, but basically, it's still the data model that we have there. So some kind of data, I call that entities. People are always set up, and it's a domain model. I say it's a data model. But anyway, and so for some reason, we always start with that. And so we do that here. We have a customer, we have a product, we have order with relations in between, some attributes in there. It's not so important at the moment. And then we have that, and when we go on and say, yeah, but we need to have services. And what usually happens is then we take the domain model and wrap that with entities, with services. So the entities with services, which is then, yeah, let's have a customer service and a product service and an order service. It's each one with its own database, of course. Somehow it always emerges this way. And yeah, there are these users connections in between. And then we think about the functionality and say, oh, well, what are we going to do with that? Yeah, let's spread that up over the services somehow. We already have these services. So search and show, yeah, that's dealing with products. We'll do it here. Putting into shopping cart, that's something related to the orders. Okay, let's put it here. And then we come checkout. We need all of that for checkout somehow. It doesn't work very well. So let's create a process service for these more complex use cases, which is a use case which touches more of the base service that we already have. So let's create a checkout service. And then we go for shipment and say, yeah, same story. So shipment service, and then we look around and say, is everything done? Oh, how do we update this information? We still figure out, so at the data maintenance use cases, like product catalog maintenance here, and okay, customers should update the information on their own, so customer self-service over there. And here's our design. By the way, I just released a slide deck a few weeks ago, and then immediately, and tweeted that, and I immediately got the Twitter response, oh, we just did that design. Oops. And it looks nice. So, I mean, it's innocuous, isn't it? So we have seen that all the time for 20 years or something like that. But the question is, how good is that in terms of remote communication? And if we take some kind of sequence diagram and look at that, oh, there's quite a lot of services which need to be up online and running, and a lot of communication in between, and quite some requests. So latency will probably hit a bit, and availability won't be too good. And shipment, same story. So the use cases which are responsible for making money and customers happy are probably a little bit slow and probably a little bit error prone. Fortunately, our data maintenance use cases are just running on one service, so they're fast and robust. So yeah. Or to put it in a little bit more ironic way, congratulations, you just designed a system for a company that's core business purpose is to maintain data, not to make money. Cool. But let's be honest, nobody will ever willingly design a system in a way that it goes against the business goals of the company. Nobody is so dumb. They had all best intentions. So what went wrong? Basically what we have this redundancy in maximizing reuse. And if we have maximizing reuse and look at the data model, we start to split up by the data model and reuse the customer data and reuse the product data and reuse blah, blah, blah. And then we apply traditional OO practices. I mean, we trained that for 30 years. Meanwhile, after going from functional decomposition, we just went to OO design. And unfortunately, if we apply them the normal way, I mean, there are better ways to do that, but the usual way, we end up with quite a high coupling and a moderate cohesion. So cohesion, I mean, we just sort the functionality in. So it's medium cohesion, which is okay for CRUD-like applications. Still, I would use scaffolding, scale frameworks, or generators for that. I mean, with a generator like we did in the 90s with Power Builder, an application which a Java or C# development team in an agile process would take 2 months to deliver it. We delivered that in 1.5 days. Straightforward. It doesn't look nice, but it didn't look nice, but well, it did its job, so and it was just for some data maintenance in the back office. That's cool enough. Single process applications inside a process, that's okay. On distributed context, well, doesn't work too well. Which leaves the question, can we do better? And if yes, how? And I usually, before I look for the next silver bullet on the horizon, I tend to look back if there were some of the elders who already did a decent job in solving the problem for me. And so I did a little bit of research. And I already talked about that cohesion and coupling thing and said, yeah, look into that paper, Structured Design, 74, Stevens, Myers, and Constantine. This was the paper which introduced the concept of low coupling and high cohesion. And I read a little bit into it, and it's basically said, yeah, fewer and simpler connections, the easier it is to understand each module without reference to all other. Yeah, that's cool stuff. We need that for maintaining our code base in a better way. So it's, yeah, but it doesn't solve my problem. And then I read on and said, minimizing connections between modules also minimize the path along which changes and errors can propagate. Now we're talking. Okay, let's dive a little bit deeper into that. What's this coupling thing anyway? Coupling is a measure of the strength of the association established by connection from one module to another. So how tightly the replace module in our context with service are interconnected. Okay, and they also added some kind of contributing factors. So the first two ones are still relevant. It's, do we have a very simple interface with few parameters, which everybody understands, or are there tons of parameters and lots of calls and stuff like that? Usually low coupling, high coupling. Then, back then they called that to module by name and to internal elements, the dependencies. So today we would say depending on interface or depending on the implementation. Yeah, we know that we shouldn't depend on the implementation. And It's not so important, that one, so let's leave that out to save a few seconds. We need the time for other things. But if we look at all that stuff, we say, yeah, it's interesting, but does it really solve our problem? And there's something important if you read old computer science paper. You need to realize this paper was written in a very different time and a very different context. Back then, they had the problem how to organize their code to not end up in a big ball of spaghetti. They weren't even thinking about distribution back then. Still, they figured out some timeless concepts. So the concepts are timeless, like low coupling and high cohesion, but the concrete instructions, we have to rethink them in our current context. I did that for a second, said, which kind of contributing factor would help me in my service situation? And I added this idea of functional independence. So the ability of a service to complete its task without another service being present. If I'm completely independent, I don't care if that other service lives. Perfect. If I have a plan B, if the service is down, this graceful degradation of service, that's partially dependent. So it's still okay, but not so good. But if I'm dead, if the other service is dead, I've got a problem. So that's not good. That's a high coupling. And before we move on, just a little word about cohesion, because that's also important to know. Basically, there's a set, yeah, coupling is reduced when the relationships among elements, not in the same module, service, are minimized. And there are two ways to achieve that. One thing is we look at the boundaries and try to reduce the surface of communication. And another thing is that we try to put things that are highly interrelated on a functional level into the same module, into the same service. So increasing the cohesion inside the service, which makes the probability that on the boundaries we have a low coupling higher. So it's just a supporting property of a service, high cohesion. It's not a required one. The low coupling is the essential thing. Cohesion just supports it. So if you can go for cohesion, it's okay. If cohesion is not that perfect, as long as you're not violating the low coupling on the boundaries, everything's fine. I also looked into another classic one. It was quite interesting to revisit that one because everyone who talks about service design and traditional computer science papers always comes up with that one. And when I looked into that one, that's quite interesting. Introduced basically information hiding separation of concerns and then says, yeah, again, different contexts, makes maintainability of code a lot better. So, and then looked into the instructions how to get that, how to implement that, and I figured out, oh, this would lead to nano or pico services. It's not exactly what we want to have. So this paper alone wouldn't help. That was very interesting for me to figure out. You still need the low coupling as leading principle. And then these principles can help you on the way to get it implemented. But if you just go for this and the implementation instruction, you would end up in pico service hell. That's not where you want to be. Okay. But let's wrap up the research part. So high cohesion, low coupling, right way. We can support that with separation concerns and information hiding. Very important, do not follow the paper instructions blindly because different contexts, different problems which they solved. Here in our context, this would lead to nano or pico services. So the opposite of what we try to achieve. So we would maximize the number of remote calls, and that's exactly not what we want to have. So rethink, but still go with the timeless principles. And if we rethink that, I came up with that functional independent thing, which reduces the risk of vertical decomposition. Okay, that's a new term, sorry about that. What's vertical decomposition? So if we have a piece of functionality which is used in several ways, we have basically two ways to split that up into smaller chunks. One is vertical decomposition, so creating some very basic elements and then compose them to a little bit more powerful and compose them until on the highest level we get enough power so they're powerful enough to satisfy the original request. And the other way is basically segregate them horizontally, so this pillar-like, so independent pieces of functionality. In practice, yeah, we typically use both of them in some kind of combination. And they have different properties. I mean, over there, the vertical decomposition, that's the uses relation, reuse and avoidance of redundancy driven, all that stuff, which creates a strong coupling. Always be aware that reuse is the strongest form of coupling available, because reuse means if the reusing piece of functionality, if the reused functionality is not available, the reusing functionality isn't going to work, period. That's it. And so inside process boundaries, it has value, definitely. Outside, so across service boundary, it becomes problematic because you have this very strong coupling across remote communication. You don't want to have that. So avoid that in service design. Horizontal decomposition, function segregation, is more like for going for autonomy and independence. This creates a rather low coupling because all these chunks work independently. They don't need the other chunk to do their job. And across process boundaries, it's a very useful pattern. Inside can also still, in terms of reuse, it's not that good, but that's okay. But still, we want to have a system which is available in production. So reuse has a value, and it's important to a certain degree. But perfect reuse and a non-running system production isn't what we want to have. So, okay. And before we move on, just a little warning. And that's very important to understand. Vertical decomposition is everywhere. We were taught that, we learned that in our computer science education, divide and conquer, most of the OO practices and so on, layering and blah, 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 blah. We also see that in our daily work, so even if we go to a meetup, dry, they always say, don't repeat yourself, and reuse things and so on. Even your IDE support that, there's a method that looks similar in two places, let's extract method and reuse it and so on. So it's everywhere. If I wake you at night and say, do this design right now, you would use that one. So it really takes, most people, it takes energy not to apply vertical decomposition. So our brain would really have to, that's hard, I have to reason about that. Couldn't you just use vertical decomposition? It's easier for me, for my brain. So our brain tries to save energy all the mode. We're in a constant energy save mode. That's how our brains are running. That's part of our biological predisposition. And most people never learned how to use that. So it's very hard to get there. How can we get there? And we all know there's another fashion whenever it's about microservice design these days. Domain-driven design to the rescue, because domain-driven design solves all your problems. So do a little bit of event storming and then apply some domain-driven design on that, and magically all your design problems will be gone. At least that's the impression that I sometimes get from some conferences. So don't get me wrong, event storming is a cool technique. If you have never heard about that, look at it, it's worth it. Domain-driven design is a cool book and cool ideas in there. If you never heard about it, read it, understand it. But is it the panacea, the silver bullet? I say, nah, I don't think so, because most people, if they go for that book first, which is still the classic, I mean, the community went on from that. Meanwhile, they moved on a bit. But usually if you go for that book, and then you read the first half, and it's a little bit dry to read, and then you never read further. And the first half is basically traditional OO design. A bit better, in a good way, but still it's traditional OO design. So usually, when we just apply that, we end up with the example of the design we've seen in the beginning. Especially there's a service pattern which exactly leads to these shipment and checkout services. So, more complex things, let's create a process service for that, anti-pattern. So there are two patterns which work quite well, conceptual contours, which nobody knows about. It's hidden in the second part of the book somewhere, but usually a little fine-grained, and bounded context, which also supports that, where everybody talks about, but usually a little bit coarse-grained. And so, yeah, it's a cool book. If you don't know it, read it, but just reading about a few patterns is not that panacea. And especially because what I've learned is that people read books like that, read the patterns, and then blend that with what they know from before. And so basically they take their old functional decomposition techniques, which they blended into OO techniques, and then blend them into DDD techniques. But in the end, they're still doing functional decomposition. But gave it new fancy names. Oh, it's aggregates now, and it's a bounded context, and blah, blah. But they're doing the same stuff as they did 20 years or 30 years. Thanks for nothing, Uwe, you didn't solve our problem. So, what can we do now? And here's the core slide of the whole talk, how we could do better, how at least, which works very well for me. For good service design, start with the behavior, not the data. And now you might say, are you serious? You were talking for 35 minutes to give us this single slide? Yeah, I'm serious, I'm dead serious. Because maybe 1% of all designs I've ever seen in my life, and I'm out there for 35 years now, more than 35 years. I think it's 37, 38 meanwhile. Maybe 1% of all designs I've seen started with behavior. All others started with the data and looked like the first one. And I still see it now all the time. Of course, domain-driven design. All the same. And so let's try to apply this idea with this case study to see how it works. So core reasoning is, just to get the thread. So we try to reduce the number of remote calls. For a given functionality, we need to, we try to need that, for given. And to do that, we need to spread the functionality between the services in a way that a single use case or a single user interaction, I see the parts of a use case where a user interacts with the system, less often needs to cross service boundaries. So we start from this use case idea or user interaction idea. And therefore, we do not try to organize our service around the data objects, but around use cases or user interactions. So how would that look like? So here's our use case diagram, basically. I also added the actors. They give me some more options if I do some more ideas when I do design as an architect. But this is what we are looking into. And again, this in hindsight design approach. How can we approach that? So we focus on minimum cross-service communication inside a single use case or user interaction. And then it starts very simple. Each use case, each user interaction is a service candidate. So candidate. Yeah, all service candidates. Not necessarily service. And then we look into the one direction. Maybe some of the use cases are just too big to put them into a single piece of code, into a single process. So maybe we need to split them up, but still use the same heuristics we talked about as before. So if we need independent deployments or if we have very disparate NFRs. So microservices may be a little bit bigger. It's not that bad. So that's okay. And then look for functional clusters with low coupling in between. Let's apply that here. Because the scenario is so simple, we're not touched here by that. If you would go for a real grown-up e-commerce system, probably would have to split up things a little bit here. But here it's okay. And then let's go the other way. Maybe it's still too small, the whole thing, so it's too small, so maybe we can combine some things. Okay, it reduces our cohesion, but we've learned cohesion isn't the important thing as long as we do not violate the coupling. So, for instance, replicating data and reconsolidating K-data across distributed systems is always a pain. And so maybe let's look for that. This is a good idea. And so, let's add the data for that product. So we split it up a little bit. So the product data go here. Here's the inventory data part. Here's the product data part, which is needed for shipping order, buying order, and so on. And then looking at that, and we see, both are working on same data. But now it's not mandatory that we put them together. Let's fire up our brains first. and reason about it. That's important. Thinking is an important thing inside design. So what's the reasoning I would be doing here? So I say, yeah, it's the same data, so maybe putting together, but different actors acting on that. So yeah, it's not mandatory to put them together. But overall, I think the option to work on a single product catalog database is, for me, more important, so it outweighs the different actors. So yeah, I would go for uniting that in one service. Still, it's not mandatory. If you have a different context, a different setting, you might end up with a different response or with a different decision. But here I say, yeah, I unite that and still have, assuming the same architectural style, basically. And then we move on and say, is there anything else? And so we have this product catalog service now. You see, yeah, shopping cart is basically a preliminary buying order. Does it make sense to put those two together? And yeah, reasoning again. Yeah, sequential cohesion, work on the same data, but still, And here the decision is harder from my point of view. So there are a lot of other aspects I have to take into account, like how different are the actual representations for a shopping cart and for the order? I mean, we never drilled down to that here in our example. Or is the UI part of the service so that we have different UIs? And we also didn't talk about the payment. I mean, that is just a remote call here. But usually payment is very important and makes this checkout part very complicated, while shopping cart should be quite straightforward. So maybe, yeah, we don't know if it makes sense or not to put them together. Here, I just assume that after all that pondering, it makes sense to put them together. But it's, again, could be different. Think about that in your context. There's no automation in there, no magic. So we have that order creation service here. And then some more things to think about, like buying order, shipping order. Should we also unite these things? And yeah, personally, I think that they have less commonalities than shopping cart and buying order, because shipping order is basically just an ephemeral entity. I mean, I just have to create that once and then make sure that the shipment is done, and afterwards I basically can forget about that. And it's just a lot less attributes than I have in the buying order. And we have also different actors, and so my decision would be, yeah, let's keep them separated. So, but we still need a signal mechanism in here so that whenever we create a buying order, we have to signal, okay, here's a shipping order. Create a shipping order for that one. But we can use different mechanics for that one. And then updates items in stock, because we dragged out the inventory data. And so the product catalog maintainer can no longer maintain that, but we still have, we have to make the warehouse employee responsible for that, which is more reasonable anyway, because they see if anything's there or not, or if anything new was delivered or not. If I'm somewhere in the office, somewhere in the headquarters, I don't know what's going on in the warehouse. So use case, fill up inventory. And so I end up with that one, which looks interesting, a bit different than the other design. But the important question is that design any better? So let's look at this in terms of remote communication. Let's check out service. Yeah, we have to go for the payment provider we said before, but that's basically it. And that's warehouse service. Looks better. I mean, all the other use cases, the data maintenance use cases, are all in one service anyway, so now we ended up with all use cases robust and fast. Still, it's not always that nice and easy. And that's where usually talks end and says, and they lived happily ever after. And unfortunately, I also have to end here, because I still give you a little idea about that. Now the question, if you really want to be serious in terms of architectural work, is, are there any trade-offs? And hell yes, there are. So just to make one thing sure, and I want to basically end with those two things. The two laws of architectural work, the first law of architectural work is every decision has its price, no decision is for free. So if anybody comes along and will say, do this and everything will be fine always, stop listening. Every decision has its price. So there are always downsides, no matter what you're doing. And about the downside, that's the second law of architectural work, we can only evaluate those decisions in our given context. There is no option that is good in all contexts. So just people in my company think that I hate Kafka, for instance. I love Kafka. Kafka is a really cool tool, but they always try to use it in contexts where it doesn't make any sense. And so I have to talk with them and say, yeah, have you ever pondered the consequences of doing Kafka here? And then we discuss that for a moment and say, yeah, well, I think we go along with a lot simpler solution or something like that. Because you can only evaluate that in a given context. So Kafka is a cool tool, but not everywhere. Same true for every other solution. Okay. So wrapping up, unfortunately, before going through all the trade-offs, think at least twice before you separate functionality, strive for low coupling, and the magic is in the behavior, not the data. If you just keep one thing in mind from this whole talk, that's the one sentence to keep in mind. But be aware it's hard to do this design because that's horizontal decomposition, which we haven't trained so much. And value the timeless wisdom. Whenever you have a hard problem, don't always look to the horizon for the silver bullet. There are lots of silver bullets, or at least good advices in the past. Go for them. So again, sorry for not giving you the trade-offs. Hope that I still gave you a nice idea about that. You can find me on Twitter. You can find the whole slide deck on Speaker Deck from that. I will try to look into the questions later on, and for everything else, just get a hold of me on the conference. I will be happy to answer any questions. But for now, thanks a lot for your time and your patience.